So what I'm gonna do here is I'm simply gonna use a component. I'm gonna start by creating just simply a geometry. And I'm gonna go and say new design modular geometry. I'm just turning the background to white so you can better see it. You don't need to do that step. Okay, so here I'm just gonna create simple, gonna make 2 lines at least. So I'm gonna create my points. So I have 2 points along the x-axis. I'm going to create a 3rd point. So here are my 3 points. I'm going to create lines between the points. So my first line, apply, generate, and I use add material. So if I look here, I created one line body and I have 1 part. If I go and create another line body, another line from points, if you look here at the detail view, it is showing add material. So this is the one that we're gonna switch to add frozen to make sure I create a distinct line body. When I use the add frozen option and I go generate, I ended up with a 2nd line body, but this made 2 separate parts that are not connected. That's why it says here 2 bodies and 2 parts as well. So the question is, how do we make these one body? How do we make these one part? And the reason, again, we're doing this, because these are going to be connected to 2 sections. So if I come here to concepts and do a cross section, and let's say we're going to make this for a change, I'm going to make this a rectangular cross section. And my first section is going to have a base of, let's see here. So the base, I'm going to leave this as a 0.01, and I'm going to make the height 0.5. let's make this point 1. So I have a rectangular section here, rectangular 1, and I'm going to make another rectangular section. And I'm going to make this 0.05. And let's keep this 0.1, but I'm going to make the height 0.3. So I have 2 rectangular sections. To line body 1, now I can attach rectangular 1. And to line body 2, I can attach rectangular section 2. Now, please note when I'm using a rectangular section, and I did mention that in a prior lecture, when I'm using rectangular sections, the check marks are yellow because I have not yet set alignment. If I go to view and show my cross sections, let me zoom in a little bit here. You see the way that these are oriented. They are oriented more like a bookshelf, where the base, the base is wider than the height, simply because when I defined my cross section, it was defined in the XY plane, Y being the height. By default, ANSYS align the Y axis in the Z direction. So the Y axis is aligned in the Z direction. Should I want to do anything different, I will go to the line body and right click on it, and I will say select unaligned body, and I can come here and I can choose to orient the section Y axis, and instead with the Z axis, I can do it with the Y axis. So I can come here, and if I do by selection, I come here, I can choose the Z axis and say apply. You see here, I think this will be very clear, the different orientation. This one is taking the default orientation. Line body 2 is going with the default orientation. And line body 1 is now oriented, and you see the check mark changed into green. If I also want to change the orientation for the second line body, I'm going to right click, select unaligned body, and I'm going to go for the Z axis also, I'm sorry, the Y axis also, apply, and it flips it. So now if you look at it, both of them are going to be, if we have vertical loads, and if this was a beam, they're going to be loaded along their Y axis. So back to the question, how do we make these line bodies? Whether they are 1, 2, or I mean, whether they are 2 or 3, the concept is the same. I'm going to come here from the tree outline and use the control button to select the 2 or 3 or 4 line bodies. Right click and say form new part, form new part. When I do that, I still have 2 distinct bodies, but I combine them together to form one part. Does that answer your question?
Yes, it does. Thank you very much.
My pleasure. Okay. Good. Again, if anyone else has any question, I'll be happy to take it for the benefit of everyone.
I have a question. I was wondering if you could briefly go over sort of how to apply the loads. I just want to make sure that I've done it correctly for homework 7, because I know there's sort of like torsional forces. I don't know if we apply those as like force loads or if there's a way to apply like a torsion in ANSYS.
Yeah, Devin, what's a torsion?
A torsion is just a force offset from the radius by some distance, or offset from the center by some radius.
No, I mean, any force that's away from a point is going to develop a moment, right?
Correct.
Go back to statics. So a torsion is really a moment.
Okay, yeah. See that that was how I was thinking about applying it, but I wanted to make sure.
Yes. So if I take, let's say, the geometry I just created, I'm gonna take it to ANSYS. So I'm launching here, I'm sorry, yeah, mechanical. So I'm starting here mechanical. So this is the part we just created, correct? So of course, our shaft is circular, but that's not a big deal. If I go to static structure, and let's say, imagine if this was the overhang, and I want to put a torque at the very tip here. So I will go to my static structure environment, and because a torque is a moment, it is not a bending moment. Like if I'm looking at this beam, what's a bending moment typically to what we are used to? That would be a moment about the z-axis, right? This is the bending moment. This is what's going to cause this beam to bend. So let me demonstrate that. If I come here and simply apply a moment, and I'm going to apply this moment to the vertex on the outside. So I'm going to select this, and then I'm going to go define the moment using component. And I'm going to show you here that I'm putting a moment about the z-axis. So I'm putting 100 Newton meter. Oh, I didn't accept this. Apply. Okay. So what I just doing here, I'm applying, this is a bending moment. You see tension at the bottom, compression at the top. This is a bending moment. If this was just a simple cantilever beam, I would also have this fixed at the left end, apply. And what I'm doing here is that I'm simply putting this beam in bending. Okay, if I come here, generate a mesh. Here comes my simple mesh. Now, if I'm gonna solve this to look at how it is gonna deform. So if I come here and just simply, beams. So I'm gonna come here and look at results and look at the bending moment. And I'm gonna come here and look at torsional moments. So I want you to realize that in this problem, I'm not applying any torque. I'm using a moment, and I'm not applying any forces. So this is like a cantilever stepped beam that is subject to a bending moment. So this should go in pure bending, And what I'm looking here is to look at the total bending moment, torsional moment, and we can also look at, to prove the point, the axial force. Let's look at shear force as well. Okay, and let's solve quickly this problem. Let me turn the sections off so we can see it simpler. Indeed, this is bending, and I'm getting tension at the bottom, compression at the top. But what you're looking here at is shear force, and you see the shear force is almost a zero. I think this would be more meaningful if I look at the total bending moment. At all times, the beam is subject to this 100 Newton meter that I applied. Let's look at the torsional moment. You see, it's all zero. So this one is not in torsion. Let's look at the axial force. It's perfect zero. So while this beam is in bending, that's what we get to see, the bending. If I look here at the deformation, and let's look at the total deformation of the beam. So for it, see, I'm getting maximum deflection at the free end, and I'm getting zero at the fixed end. So this is a simple cantilever beam that is going in bending. Now, to demonstrate what we want to do here, I'm going to go to this moment. And instead of having this moment applied about the Z axis, I'm going to put it as a torque. And a torque is simply a moment about the axis of the beam. So this would be the axis of the beam is oriented along the x-axis. So instead of applying 100 Newton meter as a Z component, I'm going to apply 0 in the Z direction, and I'm going to put 100 as a torque. And you see here, now this is showing as, you'd see it now if I go to the X direction, and you can see this is a torque, right? It's a moment about the X axis. If we look here at an isometric, you can see it going around the X axis. So now this is a beam that is subject to a torque. Let's solve this problem and see what we get. Okay. Now I have a solution, and I'm going to look at the beam like we did last time. If I look at the total deformation, look at this. If I play the animation, the beam is really going nowhere. It's remaining, is just spinning, right? I wouldn't say spinning, but it's twisting. That's the right word. Because definitely I cannot allow the beam to spin when I'm running a static structure analysis. And this is the reason when we had the bearings, I never used a fixed support like I'm doing here. I cannot use fixed support for my shafts because the bearing do allow for some rotation in bending. Okay. Now, if I look here at the total bending moment, let me stop this and, okay. If I go look at the total bending moment, if you look at this, again, this is almost 0, 1 times 10 to the minus 8. So I'm not really seeing any bending moments because this is not subject to bending. But if I go to the torsional moment, this is in torsion throughout the length of the beam of 100 Newton meter. If I look to the axial force, I have a 0. If I look at the shear force, I have a 0. This is practically 0. So in this case, really the deformation is that due to the twisting and distortion of the beam. Of course, this is a rectangular section, so it really gets some distortion as well. But these are very small number as when we're looking at the total. Does that answer the question about applying torque?
It does, thank you.
Very good. More questions? No questions about supports? How do we model the bearing?
Professor?
Yes, Paul.
So just to be clear, you don't use a fixed support, but you could do a fixed rotation and let the x-axis remain free.
And why do we do that, Paul?
So the shaft can spin in the simulation.
No, it will not allow it to spin. Actually, the reason we fix rotation about the x-axis is to prevent rigid body motion. In real life, we know the shaft is spinning, but it's spinning at a fixed speed. So it is in static equilibrium. So it's okay to put this fixed rotation about the x-axis and do not expect it to do anything.
Okay.
Okay, let me take a few minutes because I think some may benefit from that and go over this here. So let's pretend that this is gonna be like a shaft. maybe let's add one more segment to it. So, okay, I'm going to go back to my workbench and I'm going to create another static structure analysis building upon the same geometry. So I'm coming here and I'm using the geometry, but that's a different one. So I'm going to come here. No, I cannot use the same geometry. Okay, let's get rid of this. Let me save this first. So I'm gonna come here and we want to do a few things. I want to add at least one more point. So I'm gonna go create and I'm gonna create a point and we're gonna use manual input and I'm gonna go to so we have 8. So let's go another. So I have a 4th point and I also want to add another line. So I'm going to go concept, line from points, and I'm going to create this line, define this line. Wow. And please note there is add material here. If I generate, it leaves this as a part and it creates this separate line body, which I want to have a different line body to allow me to do different sections. But I will come here and make sure to, instead of having to combine these, because I mean, if I come here and combine these like this, I can come here and say form a new part. So what I'm doing here is I created one part and I have 3 line bodies. Okay, and I can come and make sure I select the section. So let's say I'm gonna select rectangular one. Again, I'm gonna fix the orientation. So I'm gonna go select unaligned and I'm gonna go with the selection method. I'm gonna select the axis and I go apply and we're all good here. So I created 3 line bodies that formed one part, and I'm gonna pretend I'm gonna use this as a shaft. Of course, I wouldn't like to use rectangular sections for a shaft, but I think this would be okay with demonstrating the concept of supports. So I'm gonna go to Workbench, I'm gonna update my project. I'm gonna double click on the model. And here we come. Now I have these 3 line bodies. They have different section. I'm gonna go to my mesh and I'm gonna generate a mesh. Here is my mesh. Now I'm gonna go to my static structure analysis and for sure, I wanna get rid of the fixed support. So I'm deleting the fixed support. I'm not gonna use any fixed supports. When I say fix here, and maybe this is something important to mention. Can you all see my notepad?
Yeah, we can see it.
Okay. When we are working in ANSYS, we are working in the X, Y, Z plane. If I look at a beam that has two vertices, how many degrees of freedom this beam element will get? If I wanted to describe the displaced state of the beam, and back to the concept of the finite elements, I'm gonna need 3 translations and 3 rotation at each node. So for each node, I'm gonna need an X translation, a Y translation, and a Z translation. So X, Y, and Z, as well as an X rotation, a Y rotation, and a Z rotation. So this is going to be at node 1. Likewise, at node 2, I'm going to need 6 degrees of freedom in the X, Y, and Z. These are to represent translations. Then I get rotation about X, rotation about Y, and rotation about Z. When I use a simple support, this is restraining X, Y, and Z translations. That's a simple support. Versus a fixed support, restrains all 6 degrees of freedom. X, Y, and Z translations and rotations. Now, there is also this fixed rotation only. And this allows you to choose the rotational degree of freedom to restrain. There is also this displacement option that allow to define specific translation. When I say specific here, you define whether this translation is in X, Y, and Z. So these are kind of the different types of supports that we've been using. So when I'm trying to model a bearing, I have to ask myself, what is a bearing doing? And I have to say here using beam elements specifically, because when we do solid elements like what we're supposed to be doing today, it's going to be different. So modeling a bearing support using a beam element. So if I have a shaft, that is supported by bearings. And when this shaft gets loaded, it can have forces like you had with the homework number 7. It could have forces in the Y and the Z. So this could be X, and this is the Z direction. So you could have forces like this. And on top of that, it also had the 1000 torque applied, and we had it going like in opposite directions like this. So what do we expect, or how do we expect this shaft to behave? As a result of the load, I'm expecting this shaft to go in bending as much as well as twisting. So maybe this shaft is going to deform like this. And the one thing I want to emphasize here is while these bearings have some width that is partially restraining the rotation, the shaft still gets to rotate about the Z-axis and about the Y-axis. So if I am to model this shaft using beams, we did have a vertex here, a vertex here, a vertex here, and a vertex here. And then we did draw these lines between the vertex. I apply the loads on the vertices, forces as well as torques. And again, torques are simply moments about the x-axis. I would like to capture the behavior that I'm seeing here. So when I looked here, if this is my y-axis, I want my shaft to be able to give me this rotation about the y-axis. So this is what I want to show, is I want to get this theta z about the z-axis. I also want to get a theta y. But if you think carefully about the spinning is not really a theta as far as the formation. The spinning is going at a constant speed, which we agreed that in this case we're doing a static structure analysis, and these two are equal and opposite. So primarily there is a twist in this portion. So yes, in this portion between the torques, there is this twist. So this could be a torque diagram. Which in this area, there is a twisting between the two torques. So when we thought about putting supports here, I said this roller, this bearing is not allowing my shaft to go anywhere as far as translation. So it is okay to come here and put or apply at this end a simple support. To restrain translations. And when I say translations, I mean X, Y, and Z. And I would do that, of course, at the two bearing location. Now, these simple support would allow for this rotation, but would also allow the shaft to spin because they are both on the same line. So I'm gonna put two simple supports. So if I'm gonna come here and put like a simple support like this, I'll come here and put a simple support like this. So we use a pen to represent that simple support. Please keep in mind that these two pins are not allowing the shaft to rotate about the Y direction. So that is not allowing the shaft to rotate about the Y direction because it's holding it in place in the Z direction. It's also holding it in place in the Y direction, so it's not allowing the shaft to rotate about the Z axis. But because both of them are along the X axis, the shaft can spin, which would not allow numerically to run a static structure analysis. And that's why we say we are gonna add away from this area. Where torque is present, and typically at the end point where there is a simple support, we apply a fixed rotation to restrain rotation about the X axis only. And I cannot emphasize only enough, because if you end up restraining rotation about X, Y, and Z, you literally made this a fixed support. But I cannot use a fixed support because I want to see this behavior for the shaft. And when I say the X axis, I'm going to write between brackets here, the shaft axis. That's the whole idea. Do you all conceptually see that? Okay, let's go to ANSYS and see how we're going to apply that. So when I come to ANSYS here, I'm going to go to my static structure and I'm going to quickly look for supports and do simply supported. And I'm going to pick vertex, do another simply supported, and pick another vertex and see apply. So now I have two simple supports. Next, I'm gonna go to supports. I'm gonna go for fixed rotation, and I'm gonna apply one here. And I wanna look at the details of a fixed rotation. And I'm not gonna leave it the way it is. I'm gonna free rotation about Y, and I'm gonna free rotation about Z. So I'm only restraining rotation about the X-axis. And I want to tell you that this is really not going to affect the results, and we're going to prove it. Okay, so I want to put it here, apply. So we're good. So now I have my supports. I'm just going to make up some loads. This moment that we had. So I'm going to apply a torque here, apply. And I'm going to leave this 100 Newton meter. I'm gonna next go to put another moment. Here, and I'm gonna use components. And my moment is about the X-axis, and I'm gonna put a minus 100. And let's solve. Invalid assignment. Okay, I have something here that yeah. I'm checking and I'm looking at my line body, and this line body did not get a material, so I'm going to go for the default material. This should fix it. I'm running my solver. Come here and look at the total deformation. Again, it's not doing anything because I don't have any forces, but it is mainly in torsion. You look at this. I'm getting here 0, 0, and this is the segment that has the torque or had the twist. And it is really, should be the 100 Newton meter. You see here, it is below this. Yeah, so I have here the 100 Newton meter. If I look at the axial force, I don't have anything. If I look at the total bending, I don't have anything. Because I really didn't apply any transverse or loads perpendicular to the axis. If I go back to static structure and just put one simple force, apply it to a vertex, apply here, and put, let's say, a force in the Y direction. So I'm going to change the components and put a force in the Y direction of 100 Newton. And now let's try to solve. Now, if we look at the total bending moment, yeah, now the beam is going in bending. If I look at the total deformation, and please note the rotation here about the Z-axis. So my simple support allow me to see this rotation. Of course, now I would have bending moment. I would have the torsional moment. You see here in that specific segment, I'm gonna have no axial force, no direct axial force, or no direct stress. And then total shear force, I have a shear force throughout the beam. I have 61.5 going in this segment, and I have 38 going in the rest of it. I hope this further clarifies how we model bearing supports in shafts. Any other questions about anything that we've done so far in ANSYS? We're good? No more questions?
Well, I don't know if you can answer. I have a question regarding homework 8. I got mostly everything right except for when it came to the deflections, and I just wasn't sure how that was possible. I just assumed that okay, if I got my like my forces and everything right, and the reactions were right, that the deflection will be right. And I'm just wondering maybe if I'm just not doing it correctly in ANSYS. I don't know. I went to
Really,
definition.
Forrester, I'm glad you asked this question. And please don't assume that if everything is correct, that the deformation have to be correct. And I'll take you back to simple solid mechanics, right? When we learned solid mechanics, for statically determinate structure, you were able to solve any statically structured problem. Like, for example, if I give you this problem here and say I'm gonna put a pull of 100 Newton and it's fixed. And of course, I give you area 1, area 2, and you can simply find, oops, sorry, I was not sharing my, okay. So I'm looking at this problem. Fix at one end, and I have 2 segments and 100 Newton. This is a statically determinate problem. I can easily find the reaction, right? Can find R. I can find, if I cut through any of this section, I can find N1, I can find N2, right? So I really can solve the problem, but I cannot find the deformation unless I give you E1 and E2. Then you can find your deformation. Delta is equal to ML over EA. So you will notice here that these N1, N2 are were independent of area 1, E1, area 2, E2. But when it came to deformation, I needed E and A, right? So you could have the wrong modulus of elasticity. And when you have this basic understanding, you would be able to correlate or better troubleshoot where your problem is coming from. So if you have everything correct except the deformation, most likely your modulus of elasticity is not correctly defined.
Okay.
Okay.
Thank you.
My pleasure. I'll be happy to take any other questions. All these are very useful for everyone. So you're all good?
Professor, I have a quick question. So for homework 9, you're asking practically the same thing, except there's a little note at the bottom for the axial force. Can you just explain that a little bit?
Homework 9?
Yes, sir.
Okay, I think homework 9 requires you to use solids.
Oh.
And we
Are
have
we
not,
going to go over that today or Thursday?
yeah, my plan was to start it today, but I always prefer not to move on until all questions are answered. So we can get started today and we can continue on Thursday as needed. Okay, so I would ask you to just defer this question until we do solids, and if it's not answered, we're going to have chances for questions on Thursday.
Roger that. Thank you.
My pleasure. All right, so if there are no more questions, let's move on then.